Hi, I'm Shiza, and I'm currently working on a project to decode speech from brainwaves. So essentially, in this video, I'll be going through the data collection process for the natural speech, which is the audio, and then the EEG data. So the way it worked in the studies and the papers I read at a very high level, and obviously I'll go deeper into this in this video, but you had some sort of audio signal, some sort of audiobook, for example, which is what a lot of studies used, and you play this audio to the patient in the study. From there, you're basically collecting the brain data in the form of EEG data from the patient and then trying to correlate the speech that is played and the EEG data. So the model is able to understand the correlation between both of them. So to decode speech from brain waves, you essentially need the EEG and the natural speech, and you need to correlate them together. So for this data collection process, I read two papers about this. The first one I went a bit deep in just to understand how they collected the data, both for the natural speech and the EEG, and how it was played for the patient. And then for the second paper, I actually dove deep into a certain technique they used using word2vec, which is a modern self-supervised model to understand the semantic concept of given words. So basically to understand how the current word in the sentence correlates to its neighboring words in terms of its meaning and the importance of that particular word in the entire sentence or the entire video, depending on whichever one you're looking at. So the first paper I read was Hierarchical Structure Guides Rapid Linguistic Predictions Using Naturalistic Listening. So about this one, you basically used an Alice in the Wonderland audiobook. And to be specific about this, the audio that was used was actually slowed 20% to improve the understanding from the patient side. And I read this paper a while ago about how there's this huge problem if you're using BCIs, because if I'm talking at this pace to you right now, you're able to understand me, hopefully. But for someone who might have some sort of communication illness or disorder or disability, something like that, they wouldn't be able to understand it at a very fast pace. So if your data is slowed down, then it can improve the understanding from their side as well. So that's one thing. And then obviously just to get the EEG data to show up properly and not go too fast. Because obviously, if you're saying, like in this example, Alice opened the door and found it led to a small. So for all of these words, it's going so fast that it would be hard to track down the EEG data. So if you're going a bit slower, then the EEG data would be more visible. And so in this case, one metric of latency, which is like essentially the time metric that you're looking at, you'd get so many signals that it would be hard to decode the speech from them. So that's one thing. And then they also use 61 amplified electrodes with equal distance across the scalp. So you basically placed all the electrodes across the scalp and then you recorded the EEG data and from from the audiobook that you have. And again, this was done non-invasively, so you have some sort of EEG cap that you put on, something along the lines of that. So that was the one that I didn't go too deep into. But the second paper, I went a bit deep and I looked at the word2vec model that I mentioned in the beginning. So this paper is called Electrophysiological Correlates of Semantic Dissimilarity Reflect the Comprehension of Natural Narrative Speech. So these papers they seem kind of complicated. Honestly, they were, especially this one. I found that it was hard to understand self-supervised learning, especially because my background has been in computer vision. And so understanding a lot of the vectorization, making the words parameters, and then working with them. There were some overlaps and parallels that I'll also talk about with computer vision, but for the most part, a lot of this was new to me, so it was a bit hard to understand, but I'll try my best to explain it using the 5 technique. So as I mentioned, you're trying to correlate the natural speech to the electrical activity. So the subject here in this study also listened to an audiobook, and there were a bunch of different trials and experiments done with the model that they're using here. So there was one where it was just listening to a single audiobook, and in this one there were 19 subjects with ages between 19 and 38. So that was the first experiment. The second one was time reversed audiobook. So basically you had 28 speech segments in total for the audiobook, and then for the time reverse you're basically playing it in reverse. So let's say you're looking at, I don't know, Jack and Jill, right? So you have that. Obviously, it wouldn't really be 28 speech segments because it's kind of small. But if you have 28 speech segments, you'd basically end up with the last word, which would be they went down the hill, something like that. It would just reverse the story entirely. And so they did this with 10 subjects as well between ages of 21 and 32. And this was, yes, playing it in reverse. Then you also have one with a cocktail party attention experiment. So I found this pretty interesting actually, because I mean, I've never really heard of it, but essentially you have 34 subjects of, these amount of years, but the way it works is you have 300 sentences on a screen, and you have two works of fiction played into each ear. So there's one work in one ear and then one work in another ear. And so each of the works of fiction was read by a different male speaker. So what you were trying to do is think of it kind of like you're at a cocktail party and you're talking to some person who's boring the hell out of you. They're talking about the most random, boring subjects. So let's say they're talking to you, but you kind of zone out. So you still have their speech with you, you're hearing it, but you're like zoning out. You're not really paying any attention to it. On the other hand, you hear some gossip going on the other side about some random thing. So you're paying attention to that. So now it's kind of like from one side, you're paying attention to the person in front of you while kind of dozing off, but you're also paying attention to the person behind you who has all this gossip. So it's kind of like, how is the attention divided? That was the intention behind this cocktail party attention experiment. So it's kind of trying to show, can you try to listen between both the different ears, and what's the ratio of like you being able to understand from one ear and you being able to understand from another ear. So there were also questions that were asked based on both these stories, just to see how the subject performed and how they listened to both of them. So that was another thing. There's also multi-sensory speech experiment with 21 subjects, but I didn't go too deep into that. Okay, so I'll go through the methods of just normally using EEG and MEG for speech processing. So as I mentioned, I'm going to look into EEG for this, but MEG is also a data set there's two data sets that I'm using for MEG data for my decoding speech from brainwaves project, but I'll just go at a very high level. They're quite similar. There's like overlaps between EEG and MEG and the process itself, but I'll just go over it and hopefully you can generalize it to both these types of brainwave data sets. So there's two types of ways you can go about the speech processing and linear regression, to be specific. So there's one thing called a temporal response function. So the temporal response function is basically going from the speech that you have to the brain and the measuring. So in a temporal response function, you're going forwards, right? You're predicting the neural response, the EEG recording from the novel stimulus, which in this case is the speech. And this allows for a detailed explanation of how this stimulus basically is encoded into the brain and then measured. And so here, when you have a speech, it sends it into the brain, and then your neurons just fire like in random parts of the brain. And so that's why you need a bunch of different electrodes on your scalp so that you can basically collect all of the data, all of the EEG data needed, and then you basically measure this. So here it's again at a very high level, predicting EEG and seeing if it's what you really got in the recording. So that's one method with the temporal response function. The other method is the stimulus reconstruction. So if you know what a neural network is and how it works, you basically have going forwards, and then you have back propagation. So in a way, this is kind of like back propagation where you're basically decoding the stimulus features from the neural recorded responses that you have. So yes, you go through this, but then you are going back this time to get to the stimulus features and just trying to understand what the stimulus was. So if you give it the EEG, can you predict the stimulus that caused the EEG in the first place? And so that's the entire model for the stimulus reconstruction. So those are two approaches, but the one that they used in the paper was a pretty modern approach using the self-supervised model of word2vec. So at a very high level, and obviously I have like a bunch of things that I can explain to go deeper into this, which I'll do, but at a very high level, you have narrative speech in the form of audiobook recording. So as I mentioned, for this one, there was an audiobook. For the one before that, the paper that I talked about in the beginning, they were using Alice in the Wonderland, that audiobook. So again, you have this narrative speech, and you're basically relating the data to the processing of the speech. So the speech itself, the way to get to the brain data, you have to work with the speech for a bit. So for the speech, you basically take apart each word of the speech and you parameterize it. So you give each of the words are a parameter, and then you're basically making all the words a vector. And I'll explain how this works. So once you make them a vector, you're basically comparing one vector of word to another vector of word and seeing how they compare to each other. How similar are they if they're right next to each other in the sentence? How similar are they? What type of words are together? And then from there, you're trying to get patterns of text. So once you're feeding the AI in, the AI will basically be able to understand how common words are together. So let's say you have one vector here, one vector here. Let's say it's apple and banana. You know, apple and banana are in the same sentence. So the model gains more of an understanding that apple and banana are usually in the same sentence. So it knows that the meanings of it might be different, or there might be some sort of correlation between those words. On the other hand, if you do something like apple and airplane, you know that it wouldn't be in the same word because in all the data that you have, all the text that you have, apple and airplane usually don't end up on the same sentence, in the same sentence. So based on this, you're basically just trying to find the similarities between different words and how they would show up in one sentence or one window of however many words you're looking at. So instead of the order of words that are similar being alphabetical, so in this case, think of it kind of like a dictionary. If you have a dictionary and you say that apple and I guess you can say apron. Apple and apron are pretty close together alphabetically in the dictionary. So you can't really assume that because they're close together like that, they're going to be similar to each other. So you're not having the order of words being alphabetical, you're actually having it be based on semantic difference. So how likely is their meaning or their semantic content? So it's kind of like saying, if you think about the alphabetical example, it's like saying, I have a pet. If you say you have a pet car, that would not make sense. If you have a pet cat, that would make sense. But you can't say that car and cat are similar because of alphabetical order. So you can't say that car would be right. Instead, you would look at something like cat and dog. So that's based on the semantic content. So you wouldn't care about car. That would be given a very high loss, a high error rate. Whereas if you use a dog, then it would be given a lower error rate because it relates more semantically to the word cat. So it's basically seeing how do words share their common context and how is the semantic proximity to one vector to another in a high dimensional space because now you have a bunch of different vectors in this space. So from there, at again, very high level, you have these words from the story and you're mapping it to brain data. So after you have word2vec, you're basically finding, again, the similarities of one word to another in the sentence. So how important is one specific word to the rest of the sentence? And once you have all this, you will basically be able to generate EEG data. And all this EEG data that you have, the height of that EEG data will reflect how one of the current word is different from the others in a series of impulses. So that's essentially how it works at a very high level, but I'll be going a bit deeper into how the vectorization works for the word2vec. So firstly, you take each word in the speech, as I mentioned, and you give it a parameter and you vectorize it. So in this case, let's say I'm doing a personality test. You're going from a bunch of traits. So you have funny, cool, kind, extroverted, and organized. And you're going from a range of 0 to 50. So let's say for my characteristics, Shiza, I'm funny, 49 out of 50. I'm pretty cool, 23 out of 50. Pretty kind, I'd say, extroverted, and then organized. So you have a range for scores based on all of these traits. And then let's say you have someone named Sam. You're basically able to do the same thing for Sam, see these traits funny, cool, kind, extroverted, and organized and give Sam a range from 0 to 50 as well. So from these two people, what you can do is after you vectorize it, that's one thing you need to know. You can vectorize this sort of stuff. You can also compare this using cosine similarity. So there's a certain formula that you can use and you can basically compare both Shiza and Sam. That's what you need to know. But in this case, what's happening is you have, let's say you have a bunch of words. So in this case, you have king, man, and woman. Now you have traits, quote unquote traits, and each trait is basically this one thing, this one element, and this entire thing, this entire strip is essentially a vector. So each of them would correspond to a quote unquote trait, but in this case, you don't even know what the traits are. So you can't say that means if it's funny, if it's kind, because you just don't know the traits. You wouldn't know them in the model, but when you're actually making the data, in many cases, the feature vectors, which is what the traits are called, they're created manually by the modeler, or in other cases, the features are obtained by asking the native speakers who say these languages, so somebody who speaks English, to basically give general attributes that they consider important. So maybe for this one, you would say represents a human. So for this one, it could be a human, and they would say yes. For these three words, a human is common. So you can have that as one feature vector, one element in the feature vector. So even if you don't know the traits, you can still kind of infer. So if you had a bunch of different words and you had their feature vectors, then you could, let's say, for example, you have all of these dark blue that you see over here. You could say that all of these respond to a human or like a person. So that's why they're all shaded in the same shape, in the same color. For something like, let's say, this girl and woman, you could say that they're both female, so you could say this is why they're correlated. For this one, king and queen, you could say that they have some sort of royalty status or a very high authority in society. So king and queen would have something about the same color. So you can still infer, you obviously wouldn't know for sure, but you can just infer based on how similar these vectors are to each other. And you can also do mathematical operations with this. So if you were to do the king feature vector minus the man feature vector plus the woman feature vector, you could basically take those shades, do arithmetic with them, and then you could get something along the lines of queen. And it kind of makes sense, right? Because if you have a king, you take out the man side, and then you have the woman side instead, then you basically have a queen. So it kind of makes sense. So that's essentially how it would work. And then after that, I looked into the training to get the proper word embeddings. So to do this, in the actual training process, you have two types of vectors. You have the embeddings and you have the context. So the embeddings have a certain amount of words. So in this case, you had like a bunch of words here. Here in the actual training process for word2vec, you have so many pieces of text, so many words. And then you also have embedding sizes, which are essentially the feature vectors for the traits. For the context, it's basically the same thing. You have the words and the embedding sizes. So embeddings are when you're actually looking at the word. So let's say you have a sentence like, I love artificial intelligence. You can be looking at a word specifically saying love, that's a word you're looking at, and then you would have a certain embedding for that. So let's say you're looking at love, and then the context would be I artificial intelligence. So you'd have all those words for the context and the embedding sizes, which are like the feature vectors for those three words as well. So you have those two pieces of data. So in the step-by-step process, you're basically formulating the input and the output. The input is from the embedding matrix over here, and the output is from the context here. So let's say the sentence this time is, she saw a big tree. So the input, let's say the current word you're looking at is big. So you would say big and big. And then the output is different words that you have in the context, so the neighboring words. So it could be she, saw, tree, uh, and then in this case, we're looking at tree and snow. So comparing the input and the output, if they're neighboring words, if they're next to each other, then the label that you give them is one. And if they're not next to each other, then the label that you give them here is going to be zero. So this is kind of just showing if they're neighbors or not. And so from getting this data, first of all, you have to look at the embeddings. You have to look at the current word, and then you have to look at the different outputs that you can have. So here I'm just looking at tree and saw, but it could also be she and so first you look at the embeddings, then you take the dot product of the input and the output. So in each word's vector, let's say you're doing big and tree, for example, you're doing the dot product of both of these. And this is where I saw the overlap between computer vision and this word2vec. So over here, let's say the feature vector that you have is 0, 1, 1, 1, 0. And for tree, you have 0, 1, 0, 1, 1. So they're pretty close together, as you can tell. They have a bunch of overlapping things. But when you multiply them, when you multiply 0 and 0, you get 0. When you multiply 1 and 1, you get 1. When you multiply 1 and 0, you get 0. 1 and 1, 1, 0 and 1, 0. So when you multiply them, whatever's similar, you get a 1, and whatever's not similar, you get a 0. So it's a really good way to understand how similar are they to each other. How many overlaps do you have? And this is kind of similar to semantic segmentation, where you have intersection over union. So when you have some sort of pixels represented in this sort of format with zeros and ones, if you have 1 and 1, then you know they're going to be intersecting. If you have 1 and 0, or 0 and 1, or 0 and 0, you know they won't be intersecting. So that's what happens when you take the dot product. And then from there, you can actually use the sigmoid function. And the sigmoid function is usually for binary, which makes sense because here you're just comparing the input and the output. So when you find the dot product, let's say you get 0.2, and this is because you're not only having zeros and ones, you're having a range from, let's say, 0 to 1. So when you multiply them, let's say you got 0.2 for this, big and tree, and for big and saw, you got negative 1.11. You can't have negative numbers, positive numbers. It's going to mess the model up. So you basically use the sigmoid function, and it basically looks like kind of an S shape. You can search it up yourself. It kind of looks like that, and you basically plot it from 0 to 1. So now for big and tree, you have 0.55, and for big and saw, you have 0.25. So that's kind of like what the embeddings are going to be, the weights for big and tree and big and saw, and the difference between both of them, the similarity. So once you find the sigmoid function, you can find the error rate from that to see what the label actually should be. So in this case, it's 1, and you got 0.55. So you can basically find the error rate, and from that, you can just do normal backpropagation like you would in a supervised model. And then it's the point is to get to a certain part where the model is able to understand the semantic concepts, or the context of the words that it's looking at. So once you have, let's say, she saw a big tree, and you're basically understanding the different weights and the similarities between each word, then what you can do is create a vector for that EEG data, which consists of time aligned impulses. So again, based on how much of importance is in certain word in the entire sentence, you can basically increase the height based on that. So let's say tree is very important in this example, then you can basically give the height of the EEG data to be bigger for the word tree, just to show that because it has more importance, because it should be receiving more attention, the height should be scaled based on the semantic dissimilarity compared to the other words in the sentence. So once you have the proper embeddings from the training, you can actually do a bunch of self-supervised learning tasks. And I honestly think self-supervised learning is one of the next big things in AI, because it can really give a really good understanding about semantic concept, and from that you can try to find a bunch of modules for reasoning and logic that can help us get to AGI. And John LeCun especially talks a lot about self-supervised learning. He's very bullish about it. So I won't go too deep into this, but you can do things like next word prediction, and you can just use a bunch of the embeddings that you get from the input features, and then trying to see what the next word would be. And it's not only next word prediction, it could literally just be something in the middle of the sentence. So if you had she saw a big tree, perhaps it could say, what is this word over here? This is a blank. Then in the testing, the word2vec model would basically be able to say, okay, what could fit here? She played a big tree? No. She saw a big tree? Yes. So it'd be able to understand that semantic concept to say that saw actually belongs here. So yeah, that's pretty much it for how you would correlate EEG and natural speech. And just want to give a huge shout out to a bunch of resources I use. It was honestly, again, really hard for me to get started and understand word2vec, but I did it, and just wanted to give a shout out to the people who came up with these resources. That's it for now.